Hi folks, we're going to take a look at an introduction to the concept of vectors. Okay, so before we start, let's try to get some reason as to why we even need to bring in these objects called vectors. Okay, and I'm going to bring us back to when we studied motion in a straight line, okay, or motion in one direction. So if you have an object moving along a straight line, well, there's only two ways this object can move. Okay, it can move towards the right, it can move towards the left. Okay, now the only thing I need to designate the difference between those two directions would be just different signs. So I could designate motion in this direction as being positive, so 2 meters per second if I'm if I'm moving 2 meters in 1 second, and if I'm going 2 meters per second in the other direction, I can just designate that using a negative sign. Okay, so all we need is positive and negative to determine direction when we're working in a straight line. Okay, if I'm pushing the object in that direction, well, I can think about the force being positive. Okay, and if I'm pushing the object in the left-handed direction, I can consider that force being negative. Okay, same thing with position. Okay, if this is my point of reference, okay, where I'm measuring my position, positive position, negative position. Okay, what happens though when you move from the one-dimensional world to the two-dimensional world? Okay, so let's say we've got our object here, and say it's not just being pushed in one direction or the other, but it might have a force acting on it in that direction and another force acting on it in this direction that's not in the same or opposite direction. Okay, so all of a sudden now we realize just positive and negative isn't enough to describe the direction of these forces. Okay, so you can think the same thing. You think you're on, you've got a boat. Okay, on the water, there's a current going in this direction. Okay, there's a wind, okay, going along the same direction. Okay, basically, again, you can think, well, here, if the current is 2 meters per second and the wind is 3 meters per second, well, what's going to be the resultant velocity? Well, you're just going to be moving at 5 meters per second. Okay, it's just a matter of adding these like numbers. Okay, but let's say now we take a two-dimensional perspective. So here's your boat. Okay, and you might have the wind that has a velocity in this direction. Say the current having a velocity in this direction. Let's say the wind now is in that direction there. Okay, it's not just pushing the boat either right or left. Okay, so what we need to do is we need to find a way to deal with these scenarios when we're in 2 dimensions. And of course, if you're going to work in 2 dimensions, what happens when you're in 3 dimensions? Okay, what if you have another force acting off the paper, going off the paper? Okay, so that's our ultimate goal, is to be able to deal with these different things like forces or velocities in more than just one dimension. Okay, so let's take a look at how we do that. Okay, so now I'll take the worksheet here, and we'll start with two essential definitions, the idea of a scalar and the idea of a vector. Okay, so a scalar is just a quantity that can be defined or described using just a number. So something like time. Okay, something like mass. Okay, all you need is a number and a unit, of course, to describe things like this. Now, the idea of a vector is if you take something like force. Okay, well, if I push something with a force of 5 newtons in that direction, it's not going to have the same effect as if I push with a force of 5 newtons in the downward direction. It's going to cause a motion in a different direction. Okay, whereas time, direction is of no consequence to us. Something, elapses over 5 seconds. Okay, direction is of no consequence. Mass, direction is of no consequence. So something like force. Okay, something like velocity, where you're not just interested in the speed, the rate of change, distance over time. Okay, you're interested the speed and in a particular direction. Okay, so if I start at this point and I go 2 meters per second in that direction, I'm not going to end up in the same location as if I start at this point and go 2 meters per second in the downward direction. Okay, now this here already starts to give us a representation for a vector quantity. Okay, so a vector quantity, okay, needs to have that numerical component, because there's a difference between a force of 5 newtons and 6 newtons, or a velocity that has 2 meters per second or 3 meters per second. Okay, so it's going to need a scalar component, okay, but it's also going to need a direction. Okay, and one way in which we can represent this is with an arrow. Okay, so let's go to how we can represent vector quantities. Okay, so let's say I want to represent going in the northeast direction. Okay, and this is supposed to represent 2 meters per second. Okay, so, well, the tip of the arrow, that's the easy part. That just tells us in what direction we're moving. Okay, so what's going to represent the 2 meters per second? Well, we're going to say that's going to be the length of this vector. Okay, now, if we're using the length of this arrow to represent that 2 meters per second, that means we're going to have a scale. So, you know, about this length here is going to represent 1 meter per second, and if I've got 2 of these lengths, that's going to represent 2 meters per second in a particular direction. So one way to define or to represent vectors is using an arrow where the length of the arrow represents the, okay, that scalar quantity, which we call magnitude. Okay, that's the scalar component, and then where the vector's pointing is the direction portion of that quantity. Okay, now that's great, except, you know, we don't always want to have to, you know, set up a scale and use our use a ruler to figure out how long an arrow has to be to represent a certain magnitude. Okay, so we use something a little more, a little less pictorial here. Okay, and for those of you who take physics, you certainly would have seen this a lot. So vector, okay, will be represented by, okay, the magnitude. So let's say 2 meters per second, and for the direction we use the cardinal points. Okay, so imagine here on this vector as you create a little cardinal plane. Okay, and what we mean by that is cardinal points are north, south, east, and west. Okay, so this direction here, if it's exactly in between north and east, can be written northeast. Okay, now when you look at this letter V, we normally reserve these letter variables to represent numbers. So if I want to make sure that this represents something that is not a scalar, okay, but that represents a vector quantity, well, remember how we use the arrow as one of our representations? Well, we just put an arrow above to indicate that this is a vector quantity. Okay, now not everything is going to be exactly between north and east or north and west. Okay, what if I have a vector that has this direction here? Okay, well, again, I still use my cardinal points, but here what I do is I measure the angle of this vector from one of the directions. Okay, so let's say here, say that was 20 degrees. Okay, my vector, say u, and say the magnitude was 10. Okay, I could write as 10, and this would be east 20 degrees north. Okay, and in some physics courses, sometimes we put square brackets around that. You can do that, or not necessary. I would say if you're already doing it in your physics course, then keep doing it, but it's not necessary. Of course, there's another way that I can represent this vectors. Instead of measuring the angle from the east direction, I can measure the angle from the north direction. So this would be 10 north, and well, if this is 20, this must be 70 degrees. Okay, and the second one tells you in what direction you're turning. So north toward the east, so north 70 degrees east. Okay. Now we're going to see later on that we're going to have other ways of representing these vectors. In fact, ways that are going to be quite useful for us, especially when we're generalizing this to 3 dimensions. And hey, maybe we can generalize this even more than 3 dimensions. Okay, but we'll save that for now. Okay, we're going to start with what we call geometric vectors. Okay, geometric because you're specifically indicating how long the arrow should be, in other words the magnitude, and you're specifically designating the direction. Okay, so these are called geometric vectors. Now, one thing I'd like to look at, and this is something that's going to come up over and over again, because we can actually think of numbers, these scalar quantities, as themselves being vectors. Okay, in other words, they're vectors in 1 dimension. So I want you to think of the real number line. Okay, so here you've got 0, 1, 2, 3, and -1, -2, -3. Instead of considering this as the number 3, we can think of it as the vector going from the origin to 3. So instead of the number 3, we think of the vector 3. Okay? And you can do this with any numbers. Represent that number using this vector quantity. Now, one reason for doing this is because we know a lot of things about numbers. We know how to operate with numbers, and we're going to see if maybe our operations with numbers, okay, can help us to determine ways that we can operate with these new objects that we've defined called vectors. Okay, so I'm very often going to come back to make the comparison to the real number line. Okay. Now, here, let's look at some properties here. What does it mean for 2 vectors to be equal? Okay, well, what did we say a vector was? A vector was a quantity that had a magnitude, so numerical component, and a direction. That's it. So, if you have one vector here that has this particular magnitude in that particular direction, well, if I were to draw a vector right on top of it, that would also have the exact same magnitude and would be pointing in the same direction. Okay, but what if I were to draw this vector here? Okay, well, this vector here has the exact same length as the vector above. Okay, so they have the same magnitude, and if I were to place a cardinal plane here and one right at the tail of that vector there, by the way, we call this the tip of the vector, this is the tail of the vector, well, we see that it's the exact same angle from the east direction. So in other words, these 2 vectors have the same magnitude and the same direction. Okay, that means these must be equal. And this comes to one of the very important concepts of vectors, is the location of the vector is of no consequence. The only thing you need is for the magnitude and the direction to be the same. Where I place this vector, I could take this vector and place it anywhere on this piece of paper, as long as it has the same length and the same direction, they're equal vectors. Okay? Well, what does it mean to be an opposite vector? Well, let's go back to our number line. Well, what do we mean by the opposite of the number 3? Well, normally we think of that as -3. Okay? But if we think of this in terms of vectors, it would be the vector that starts at 0 and goes to -3. Okay? So, an opposite vector is a vector that has the exact same magnitude, but is just pointing in the opposite direction. Okay? So nice and easy on a number line. If my original vector is pointing towards the right, the opposite vector points towards the left. Okay? Whereas here, if I'm drawing any vector on my sheet of paper, well, if that's my vector v, okay, the opposite vector to v will just be the exact same magnitude, but just in the opposite direction. Okay? Okay, and just as we use with numbers to indicate to the right of the origin, to the left of the origin, okay, another thing we're going to do a lot of is we're going to co-opt notation from numbers. Okay, so here we're going to call this vector negative v. Okay, so already we're seeing a bit of an operation here because I'm taking this vector v and I'm multiplying it by, well, what does this negative really represent? Represents multiplying it by negative 1. Okay, so keep that in mind because we're going to start talking about operations on vectors. Okay, next is parallel vectors. When you think of parallel lines, you think of two lines that never intersect, or of course you could have two lines that are one on top of the other. Okay, so parallel and distinct, parallel and collinear. Okay, so it makes sense that any two vectors that have the same direction, okay, would be parallel. Now notice here, these are not equal vectors necessarily. So to be parallel, you don't have to be equal, you just have to have the same direction. Okay? But now let's think of this vector that's just in the opposite direction. Well, if you sort of make that comparison to parallel lines, well, this is also parallel to these two other vectors. So in order to be parallel, okay, you need to have either the same or the opposite direction. Okay? Now, before we move on, okay, we have this symbol here which represents our vector, and we know if two vectors are equal, they have to have the same direction and same magnitude. If they're opposite, same magnitude, opposite direction. Okay, well, it makes sense that often we'll be interested in what the magnitude of this vector is. I can see, in what direction it's pointing, but if I want to specifically talk about the magnitude, well, we're going to need a symbol. We're going to see that the magnitude of this vector is going to be very important. So we need a symbol for magnitude. Well, guess what we're going to do? We're going to co-opt some notation from the real number system. Okay, so here I have two vectors that have the same magnitude. Their directions are opposite, but they have the same magnitude. Okay, well, there's a symbol we can use that represents the distance from 0 to that number, whether going from 0 to 3, 0 to negative 3, and of course that's absolute value. So say we've got absolute value of negative 3 is 3. Absolute value of 3 is 3. What this number represents, it's a positive number which represents the distance from the origin. Okay, so we're going to co-opt this notation to represent magnitude. So how do we represent magnitude? Okay, using the exact same symbol. But notice that this here is surrounding a vector. So when it's surrounding a vector, this means magnitude of the vector. Okay, when it's surrounding a number, okay, no vector sign here, it represents absolute value. Okay, so you have to keep in mind, okay, so think back to when we used round brackets to represent intervals, and you had to understand when this notation represented an interval and when it represented an ordered pair. Okay, so keep in mind that the good thing about co-opting this notation is that we're not having to invent more and more notation, but you have to keep in mind what it represents. Okay, so we're going to start talking about this idea of operating on vectors. Okay, try to go a little quicker here. So it says here, how would you represent a vector with a magnitude 3 times larger than a vector v and in the same direction? So let's draw it here. Okay, there's my vector v, and I need something that's 1, 2, 3 times larger in terms of magnitude, okay, and in the same direction. Okay, so let's think of v as being, even 10, magnitude of 10 in the northeast direction. Okay, well, the only thing I'm changing here is going to be the magnitude. The direction will not change. Okay, so the only thing I'm changing is a numerical value. So why don't I use the notation of multiplying by a numerical value to represent just changing the magnitude of a vector. Okay, so here, okay, hopefully that didn't go dark. Well, if it did, hopefully there's light again. Okay, so we're going to represent this change in the magnitude, in this case here, wanting to make it 3 times larger by just multiplying that vector by this scalar quantity. Okay, so 3v would just be the vector 30 in the northeast direction. Okay, and what is the magnitude of this vector 3v? Well, I just need it to be 3 times the magnitude of my vector v. Okay, so this is what we call scalar multiplication, is we take a number and multiply it by a vector. So notice here, this represents a scalar quantity because there's no arrow. This represents a vector quantity. Okay, and what does this scalar do? It just increases or just multiplies the magnitude of that vector by whatever k is. Okay, so the magnitude of kv is just the k times the magnitude of v. Okay, so is this the whole story? Well, what if I multiply the vector v by -2? Well, let's see if we can make some sense out of that. Well, multiplying it by 2 just means that I'm keeping the same direction and making the magnitude twice as large. But let's remember what that negative symbol represented earlier on. We used it to represent in the opposite direction. And so that's all it's going to be. It's just going to be a combination of those two. So if this is my vector v, okay, the vector -2v will be twice as long, but just pointing in the opposite direction. Okay, but that means that our little definition here isn't going to work, because then the magnitude of -2v, based on what I wrote, would be equal to -2 times the magnitude of v. But magnitude is a positive quantity. Okay, it's representing a length. Okay, so this is not going to work out. But it needs to have a magnitude that's 2 times larger. So how can we fix that? By putting absolute values. Okay, so the actual property is this one here. But this is where we need to be careful. These symbols represent magnitude, and these symbols here represent absolute value. Okay, so we've pretty much answered this question here. I guess instead of using half as large, I use twice as large, so we can skip this here because we've essentially answered it. Okay, so this is our very first operation with a vector, except the operation is not between two vectors, it's between a vector and a scalar quantity. Okay, next class we'll see how it's going to make sense to operate with two vectors. Okay, we'll see how that's of use to us. Okay, so last thing we're going to look at is a particular scalar multiplication that's of use to us. Okay, so if you've got some vector v, okay, again, let's say v is 10 in the northeast direction. Okay, if you'd like a vector to represent essentially just this particular direction, a vector to represent that direction, okay, that you can make as big or as small as you need. Well, let's say I need to create a vector that has a magnitude of 20 in this direction. Okay, very easy, just multiply v by 2. If I need a vector that has a magnitude of 100, easy, just multiply v by 10. But what if I need the vector to have a magnitude of 27.469? Okay, that's still not too bad, since my magnitude is 10, to figure out, well, how much do I have to multiply 10 by to get to 27.269? But what if instead of 10, my vector had a magnitude of 210, and I needed a vector that was in the same direction with a magnitude of 27.265? Okay, Well, we'd have to do some work to determine what the scalar multiple that I'll need to change its length. But what length would be always easy to change? Well, that would just be a vector that has magnitude of 1. Okay? So what we're defining here is what we call a unit vector. Okay? So if it's a unit vector in the same direction as v, well, I don't want to use the arrow symbol because that's the original vector v. What we use for a unit vector is what we call v hat. Okay? So v hat is a unit vector. So what that means is it has a magnitude of 1, okay, in the same direction as v. But remember, we want to keep the same direction as v, okay? So we can do that by multiplying v by a particular scalar. So what would I have to multiply to 210 northeast so that my new vector was in the same direction, okay, but had a magnitude of 1? And hopefully you can see that what I can do is multiply v by 1 over its magnitude. So if I do 1 over 210 times the vector v, what am I going to end up with? I'm just going to end up with a vector that has a magnitude of 1, but still in the direction northeast. Okay? So the vector given by v times 1 over magnitude of v, okay, will always be a unit vector. Now notice here I'm writing it as a multiplication because that's what we defined earlier with scalar multiplication. But again, let's co-opt the notation of numbers, okay, and rewrite this as a division. So scalar division is essentially just a special case of scalar multiplication. It's just like multiplying by the reciprocal of that number. Okay, and so this is how you can define any unit vector. You take the original vector divided by its magnitude. The new vector will have magnitude 1, but will keep the same direction. Okay, has to keep the same direction because 1 over magnitude of v is a positive number. Okay, so let's just give you a quick look at what the notes look like here. So notice how we're defining scalar vector. Okay, vector notation, we'll talk a little bit more about that. How we can represent it, how we can determine or how representation of the magnitude. Okay, one thing that we'll talk about a little more to next class will be what we mean by the angle of two vectors. Okay, so here what it means for them to be equal, opposite, and parallel, and we define this idea of scalar multiplication. Okay, that scalar multiplication just gives a new vector, okay, and whose magnitude is going to be, you know, absolute value of k times the magnitude of the original vector, and depending on whether k is positive or negative, it'll either be in the same direction or opposite direction. Okay, and lastly, we use scalar multiplication to create a vector with unit 1 that's in the same direction as my original vector. Okay, that's it for this one here.